Good morning, dear students, and welcome to Vista's Learning and online educational platform. My name is Denzil, your physics tutor for class 11. Let's get started with today's session. Today, we discuss motion in a plane with a constant acceleration. This is a session 3 of the chapter Motion in a Plane. In the previous chapter, we discussed some of the physical quantities such as velocity and acceleration and how they are described in a two-dimensional plane. A two-dimensional plane consisting of x-axis and y-axis respectively. Now, we learned the components for these velocity as well as for acceleration. The components can be split into respective x component and the y component. Today's session, we will be discussing some of the equations of motion under the velocity as well as acceleration, the relation between the two, and how they can be expressed in its component form. But before we get started with writing down this equation of motion, first we take a look at a concept that is known as constant acceleration. Here is a small animation of a car that is increasing its velocity. And how can you say it's increasing its velocity? It is noted down here. Alright, so you see the velocity increases, but as the velocity increases, have a look at the acceleration. It remains the same. So acceleration for a given period of time or for a given journey is a constant. This constant acceleration can be determined by using where acceleration A, which is equals to the rate of change in velocity, and that is what we had learnt in chapter 1 as well. Chapter 1 meaning motion in a straight line. There we discussed under acceleration that it is defined as the rate in change in velocity, which is given by delta V by delta T. This delta V can be expressed as a difference between the final velocity and the initial velocity. So I represent my final velocity to be V and my initial velocity to be V suffix naught divided by the time. Since the object even in this given animation is starting from rest, so that means it starts from time where t is equals to 0. And eventually the total time for the journey is t. So final time minus the initial time, t minus 0. And you get this expression where a is equals to v minus v naught by t. Transpose the t to the other side. Not a glass of tea. Don't transpose the glass of tea to the other side. You can sip on those glass of tea if you're having tea. But then what you get this expression as AT is equals to V minus V naught. So V will be equals to V naught plus AT. This seems familiar, doesn't it? Because you have studied this in the previous chapter in motion in a straight line. We expressed and derived 3 equations of motion. We derived the 3 equations of motion using 2 different methods. One is called a graphical method and the other is called a method of calculus. So let's make note of those 3 equations of motion. One, we learned that the equation of motion is expressed as V equals to V naught plus AT. Second equation of motion, that is S or R. Okay, S is equals to UT plus half AT square. And how do you obtain this? We obtain this by defining what is an average velocity. Where you calculate this average velocity, so let me put that as AVG to show average velocity, which is equals to the sum of initial and the final divided by 2. So by expressing it in this format, you can derive this particular equation of motion where S equals to ut plus half at square. This u is nothing but initial velocity v naught. So if needed, you can express this as v naught of t. Now, our objective is to find the equation of motion in terms of its components. We want with respect to x component and the y component, since the object is described in a plane. If it was along a straight line, then this equation would suffice. But since it's a plane, we have to find its components. So to do that, we take the definition of our average velocity. So what is average velocity? Where v plus v naught divided by 2. And when this is multiplied to a given term t, you get the distance r. That is true case, right? Now, considering the displacement happens between the initial and the final, so we can express this as r naught and this as r minus r naught equals to v plus v naught by 2 times t. And what do we know about v? We just looked at the expression the previous, where v is equals to v naught plus at. So in place of v, we will substitute v naught plus at plus v naught divided by 2 times of t. So you get r minus r naught, which is equals to 2 v naught by 2 plus, and once multiplying t, so I'm going to multiply t simultaneously, a t square by 2. And you get this r minus r naught, which is equals to v naught t plus half at square. Looks somewhat similar to the previous equation that we were describing. All right, but here I'm representing as the vector form. These r and r naught are the position vectors. So you get this r, which is equals to r naught plus v naught of t plus half at square. Wonderful. So now we have obtained a relation between the position vector, acceleration. Now we have to write it in its component form. Let's take the first equation, that is writing this given equation in its respective component form. So we have the equation, which is v equals to v naught plus at, and when it has to be expressed in its component form, first we show the velocity as along the x-axis. So to explain you better, I can do that by using a graph. All right. If this vector represents the velocity, then when constructed a projection along the x-axis, so much of a distance is the component which is x component of the velocity. Similarly, extending a projection along the y-axis, the length of that vector gives me the y component of the velocity. Now, for those of you who find this difficult to understand, you can go look into my previous lecture where I explained to you about the components of velocity along the x-axis and the y-axis and how they are related to the velocity vector. All right. So considering the case that we have such an equation, we have to find its respective components, x and the y. So for the x component, all I have to do is mention as Vx, which is V naught of x plus Ax of t. Will time be a different component for x-axis and y-axis? No, time will not be a different component for x-axis and y-axis. Time will be the same for this vector v, vx and vy. So therefore, we do not write it down as t suffix x. Similarly, you can also express as y. And one more reason why don't write it as tx is because time is a scalar quantity. So we don't have to. So velocity component along the y-axis is v naught of y. So what is v naught x and v naught y? Are the initial velocity along the x-axis, initial velocity along the y-axis, plus ay of t. Good. So now we have obtained the equation of motion, the first equation of motion in terms of its component form. Can we also identify for the second equation of motion? Let's have a look at that one more time. This was the second equation of motion. So we take this and express it in a component form. R and R naught are the position vectors. So for x component, it will be x minus x is equals to x naught plus v naught of xt plus half ax t square. See, second equation of motion expressed as the x component form. Now for the y equals to y naught plus v naught of y plus half ay t square. So we only discussed with these two component vector form for the first equation and for the second equation. Why is it even necessary to discuss this component vectors? Does it have any importance? Yes, it does. So for that, we take a question. So this question is also from your NCERT textbook, from your example section. Have a look at it. We'll go ahead, we'll answer them. A particle starts from the origin at t equals to 0 with a velocity 5 I cap meter per second, and it moves in an xy plane under the action of a force which produces a constant acceleration of 3 I cap and 2 j cap meter per second square. What is the y coordinate of the particle at the instant its x coordinate is 84 meter? What is the speed of the particle at this time? So it may be a lengthy question, but first things first, make note of things that are given. What are the things given to us? Given that the velocity of the particle v is equals to 5.0 I cap meter per second. Next, constant acceleration. So a, which is equals to 3 I cap plus 2 j cap. Now for those of you some of you might be wondering as to why should it be a constant acceleration? Why cannot be a variable acceleration? If it's a constant acceleration, it is easy to assess the problem or easy to analyze the problem. And therefore, you can apply the two equations that we learned. These two equations rely on a constant acceleration. What if it's not constant? Then you consider the average acceleration throughout the journey, which gives you one constant value, and you can take that and try to analyze the problem once again. But again, there are different methods which we'll be looking in a different chapter. You have chapter that is forces. So there we will be discussing as to this acceleration that are not constant in a given cases. All right. Velocity, acceleration as mentioned. What else? What is the y coordinate of the particle at the instant x coordinate? X coordinate of a particle is given. So x of t at any time t is 84 meter. All right. So now we need to find the y coordinate, and the second part says the speed of the particle. So how do we go solving this problem? First, you have to find the coordinate. Which equation among these two will you use? Will you use the first type of equation? No, because here you do not have the coordinate. Then will you use the second type of equation? Yes, here you have the x and the y coordinate, you see. So we use the second type of equation, namely this particular type, where r equals to r naught plus v naught t plus half a t square. R naught is anyways 0 for our understanding in this problem. R naught is anyways 0. So you can proceed by writing r equals to v naught t plus half a t square. R is what we need to identify. V naught is given. This is v naught because it's starting with the velocity of 5 I cap. So 5.0 I cap t plus half. Acceleration is 3.0 I cap plus 2.0 j cap. 3.0 I cap plus 2.0 j cap t square. Then we can write 5.0 t times I cap. That's because I've multiplied t inside. It's a scalar quantity anyways. When a scalar quantity is multiplied with a vector quantity, it only changes by its magnitude. Direction will remain the same, which is I cap. All right. I hope you've understood. So to give you an example, let's say this vector represents A. Okay, this vector here represents A. When I multiply any scalar quantity, a scalar quantity like the time, let's say 2. Okay, it's a constant, has a magnitude 2. So what happens is that the vector, the length of the vector becomes larger as 2 times a vector, but the direction will remain the same. So same thing here, I can multiply t to 5.0, but the direction, this I cap is the direction, will remain the same. Okay, so this is just an example. Right, and then multiply the half. First you multiply the half, which you get 1.5, then multiply t square I cap plus 1.0 t square j cap. Bring all the I cap on one side, take the common factor which is I cap. So you get r equals to 5.0 t plus 1.5 t square I cap plus 1.0 t square j cap. this I cap and j cap are unit vectors along the x-axis and y-axis. Unit vector of x-axis, unit vector along y-axis. You could also call these as basis vectors. So this expression here, this term here is the x component, displacement along the x component, displacement along the y component. So x component, which is a function of time, is 5.0 t plus 1.5 t square. Okay. We already have x of t, 84. So by substituting 84, we have to find what is the value for t. Okay. By shifting that 84 to the other side, you get 1.5 t square plus 5.0 t minus 84 is equals to 0 represents a quadratic equation. By solving this quadratic equation, you get time t, which is equals to 6 seconds. Okay, you get time t, which is equals to 6 seconds. Now that we have time t, we can find the y component. Remember, the y component is this. So y of t, which is equals to 1.0 t square, or just t square. Now remember that displacement occurs for the same time for the x component as well as for the y component. If the displacement has certain which is of if the displacement along the x component is 84, it will be in a given time 6 seconds. Now, even if it's for a y component, the displacement for a y component will happen in 6 seconds. Therefore, I substitute as y of 6, which is equals to 6 square, and I get y component displacement, which is equals to 36 meters. See, we have found the first part of the question, the answer to the first part of the question, which is, what is the y coordinate of a particle when when at a given instant x coordinate is 84? So what will be the y coordinate? 36. Are we done? Not yet. There's one last piece of information, or one last question to be solved. What is the speed of the particle? To define a speed, we say rate of change in position of an object. Rate of change in position of an object. How can this be expressed? Velocity v equals to dr by dt. Interesting. Do we know what is r? Certainly we do. We know what is r. See, r is written here. Right? Yes. So this is the x component, this is the y component. So we have to differentiate the given x component with respect to time and the y component also with respect to time. So I'll do that for you, differentiating the x component and the y component with respect to time. So this you get 5 plus 1.5 t, oh no, that's 2 times, sorry, 2 times 1.5, 3. 3t I cap plus 2t j cap. What do we know about the time? Time is 6 seconds. So by substituting velocity at t is equals to 6, you get 23 I cap plus 12 j cap. Wonderful. So now we have found the two respective components of 23 and 12 for a velocity along x-axis and velocity along the y-axis. How do we find its magnitude? Well, let's go here. How do you find its magnitude? I'm going to write it here, so I hope it is visible to you. Magnitude of velocity, which is equals to square root of 23 square plus 12 square. And 23 square is 579. So go ahead and work it out. 679, is it? 23 square, 679. 679. And this is 144. All right. No, it's 579. It is not 679. Can one of you kindly check? Can one of you kindly check? 579. $579 plus 144. Okay, sum them up. 3. I have a wrong feeling about this. It is not 579. It's 529. It's 529, not a 579. 13, then 673. 673, which can be approximated close to 26. So the velocity of the particle, the magnitude of velocity will be 26 meter per second. Ta-da! We found the velocity of a particle. Now we need to find its direction. Direction, tan theta equals to y component is 12. Y component is 12. 12 by 23. So theta will be equals to tan inverse of 12 by 23. This will give you the direction of the object. Magnitude approximated to 26 meter per second, and the direction, which is tan inverse of 12 by 3. So this is how you solve the problem for given components of x and y. So similarly, you have one in the exercise which is exactly the same type. I want you to go ahead and try this. We'll try to solve this in the next class. So that is all I have for today. Do visit us at www.v-learning.in to get more details about the class. You can catch up with the previous classes where the concepts that I've introduced, those concepts will have a continuation in the next session. So until then, everyone, I wish you all a good day. Take care and bye-bye.